Hello, my name is Bill Kinney, and this is one of my many videos on problem solving for financial math to help people study for Actuarial Exam 2. Now you might be saying, wait a minute, I don't want to be an actuary. I came to this video because I wanted to learn about how to compute the yield or rate of return when investing in a rental property and then reselling, a very practical thing. I can make some money off of that. And if that's you, I think there are things in this video that could be for you. For example, at the end of the video, we will actually do the calculation in a spreadsheet for how to calculate the yield in such a situation. However, I should warn you that we are going to do some pretty mathematical things at first. If you can wade through the math, and maybe the math is even interesting to you, then you'll get the benefit of seeing the calculation with the spreadsheet at the end, or you could even fast forward just that part if you don't care about the theory behind it. But I think it is good to know the theory behind it anyway. What I've done is I've modified a couple problems from this book, the 7th edition of the Mathematics of Investment and Credit by Samuel Broverman, to this very practical situation. But again, we are going to do some theory first in the problem before we look at the practicality of computing it with a spreadsheet. It's kind of a long problem statement. It's longer than you would see on an actuarial exam. And in fact, because we got to use a spreadsheet and really the full capabilities and not just simpler calculator capabilities, you probably would not see this type of problem on an actuarial exam, but you could have a homework problem like this, especially if you're using Broverman in some class. And just, it's easy to get scared off by such a long problem statement. Just take it step by step. Take a deep breath and say, okay, I just need to break this down into pieces. I need to use my imagination to think about what's going on here. We've got this person, Smith, who's investing, investing in a rental property. And evidently then is going to have some renters that Smith is going to get money from. And here's the big thing, actually. Maybe this amount that Smith buys it for is going to go higher. Maybe the rental property, the investment property, is going to appreciate over time, maybe to even $1 million after a couple of years. That's possible. Smith can't pay all that $900,000 at once, but can make a down payment of $150,000 and then takes out a loan for the rest. Okay, that's typical. Most people can't pay such an amount right away, so they make a smaller payment, a down payment, and then they take out a loan for the rest. But loans must be repaid, so Smith must make monthly loan payments starting 1 month after the loan is made. He's also got renters ready right away. He's also going to receive monthly rental payments. This is evidently going to happen for 2 years. 2 years. 2 years after the original purchase date, Smith is going to sell the property for an unspecified amount. Why? Okay, so that's the background of what's going on here. With these loan payments and with the rental payments that Smith gets, there's what's called a net outlay per month of $1,200. Now that might initially sound good. It might say, you might be saying to yourself, okay, I guess that's money that Smith gets. Well, no. The way this is phrased, that net outlay is how much Smith must put out every month. Evidently, the rental payments are not enough to cover the loan payments. Does that ever happen? Yeah, it does happen sometimes. Sometimes the rent that you get from your renters is not enough to cover your loan. That doesn't mean it's a bad investment because of the appreciation, especially if you keep the property well maintained. Okay? Maybe, again, the appreciation goes from $900,000 up to $1 million after a couple of years. That's possible. 2018 is right now, it's a pretty hot housing market right now. That could happen. So it's not all bad, even though his monthly loan payments are $1,200 more than the rent that he receives. There is a practical thing here. Taxes are due, $10,000 payable 6 months after the loan is made and annually once a year thereafter, as long as he owns the property. He's only going to own it 2 years, so he's only going to make 2 payments of taxes. He's selling the property for more than the balance of the loan, so that's good. You would hope maybe a lot more. You would hope Y might be close to $1 million, for example. All right, so that's the basic setup. Here you have the mathematical things we have to do. Before we get into the math, let's continue getting our minds around the basic setup. I think it's helpful for anyone, actuary or not, to draw a timeline here. This is going to be time in months. That would be the most natural thing to do since that's when the rental and loan payments are going to be made. So we have time 0, that's when the property is purchased and the loan is taken out. Time 1 is when the first loan payment and first rental payments are due. Time 2, etc. going to be 2 years. That's 24 months. Time 24 is the last one here. What I'm going to do is above this number line, above these numbers, I'm going to put monetary amounts, net inflows for Smith, which is going to mean, for the most part, these are going to be negative because mostly he's putting money out. It's only at the end, at time 24, because of the selling of the property for value Y, that he's going to have a positive inflow. So I'm going to label these with mostly negative quantities here. And to make it easier to write, I'm going to say these amounts are going to be in thousands. In thousands. I've got 150,000. That's the down payment at time 0 that goes out of Smith's hands. I'm going to write a negative 150. Could write a negative 150K, as K is an abbreviation for thousands, but some people might not know that. I'll just say in thousands here. Okay, so again, that's the money out of Smith's pocket right away. Nothing to do with the 750,000. That's essentially going right from the bank to the seller of the property. At time 1, though, then we have the net outlay of 1,200, 1.2 thousand. But again, that's money going out of Smith's hands. He's got money coming in from the renters, but money going out for the loan payments, which are greater than the rental amounts. So I'm going to put a negative 1.2 here, and a negative 1.2 here, etc. At time 6, however, there's also taxes. 10,000 payable 6 months after the loan amount is made at time 0. 10 plus 1.2 is 11.2. Put a negative 11.2 here. Maybe just for emphasis, at time 7, I'll go back to negative 1.2 and I'll put that. 1 year after 6 months is time 18 months, is another payment of 10,000 in taxes. I'm going to get another negative 11.2. Then it again goes back to negative 1.2 up through time 23. What about time 24? I'm going to make an assumption, even though it's not explicitly stated in the problem statement, that the time 24, this 741,200 balance includes, because of this last 1,200, the net outlay of 1,200 that comes from their renters paying their rent and you paying the monthly payments. So it doesn't explicitly state that, but it seems to be an implicit assumption because those match. Now, in real life, that they wouldn't match in all likelihood. But just to make things simpler, I'm going to go ahead and make that assumption. So what is the net inflow of money to Smith at time 24? It would be Y minus this amount. Y minus 741,200. These are already in thousands, so I'll write a Y minus 741.2. Okay, so that's the basic setup. Now we get on to the math. Okay, so here's where it gets pretty theoretical. In parts A and B, we're doing theoretical math. It's in part C that we're going to get a bit more practical. We're going to use a spreadsheet to do a computation, but you're not really going to understand what's going on with the spreadsheet unless you understand some of the theory behind the math. Okay. Part A, give a mathematical reason why there is a unique monthly yield rate, sometimes called an effective monthly yield rate. Another name for yield rate is internal rate of return. That's what I've been using with my actuary students. IRR, that is bigger than -1. As a percent, that'd be bigger than negative 100% on this 2-year transaction. And then in part B, we'll be finding the minimum value of Y. What minimum sale price guarantees a unique positive monthly yield rate, I bigger than 0 instead of bigger than -1. Positive monthly yield rate over the 2-year period. It's evidently going to have to be a fair amount bigger than 741,200 in part B. But here in part A, evidently I is guaranteed to be bigger than negative 100%, which it better be, you would hope, as long as Y is bigger than 741.2 thousand. The book puts a greater than or equal to here. I think I'm going to put a greater than sign just for sake of convenience in terms of really making the math work out as nice as possible. All right, so how do we get to answering these questions? What we need to do is we need to write down a function, really, excuse me, that represents what's called the present value of this cash flow. Present value of the cash flow. present value of the cash flow is what that says. This is really going to be a function of what I'm going to label V. And if you are an actuary student, you've seen that before. This is called the present value discount factor. What in the world is this about? Money has what's called a time value. $1,000 today is worth more than $1,000, say, 2 years from now. Or let's make it 1 year from now. Why? Well, for one thing is because people are, they're impatient. They want their money now. Okay, they want to buy something right now. Another thing is that it's kind of opportunity cost. If they had $1,000 now, they could invest it in the stock market or whatever and get a return and get more than $1,000 a year from now. And for another thing, there's inflation. The value of money goes down over time. The cost of things, generally speaking, goes up over time. When you think about $1,000 growing over 1 year, say at an interest rate of 10%, you end up multiplying it by 1 plus the interest rate. Take this 1,000 and multiply it by 1.1 if I have a 10% interest rate going on. That's going to represent 10% growth. The money's going to go up to $1,100. Conversely, how do I go backwards in time? How do I take that $1,100 and discount it, find its present value times 0? I got to divide it by 1.1. Divide by 1.1 to get 1,000. Dividing by 1.1 is the same as multiplying by its reciprocal. 1 over 1.1 is 0.90 repeating, about 90.9%. So if the going interest rate on investments is 10% per year, the interest rate I, that's analogous to this IRR, would be 0.1, say, then the corresponding V would be 0.90 repeating, about 90.9%. Okay? So this is the thing that I'm going to use to discount all these amounts back to time 0. Now the negative 150 is already at time 0, so it does not need to be discounted. Just write a negative 150. This negative 1.2 at time 1 does need to be discounted back by 1 month. It needs to get multiplied by V. This present value discount factor, again, if I is 0.1, V is 0.909. The negative 1.2 at time 2 needs to get discounted back in time 2 years. It needs to get multiplied by V twice. In other words, it needs to get multiplied by V squared. The negative 1.2 at time 3 needs to get multiplied by V 3 times. It needs to get multiplied by V cubed, etc. The negative 11.2 at time 6 needs to go back in time by 6 years, multiply it by V 6 times, multiply by V to the 6th. Then I have a negative 1.2 at time 7, etc. Negative 11.2 at time 18 needs to be multiplied by V to the 18th, etc. Finally, at the end, we have this quantity, y minus 741.2, which is going to be a positive quantity because our assumption on y, even if it were negative, I'd still put a plus sign here. Y minus 741.2 needs to go back in time by 24 months. It needs to get multiplied by V to the 24th. So what I have here is a polynomial function of V. 24th degree. It's probably bigger than any polynomial function you've ever seen before. What could be a mathematical reason based on this why the yield, the internal rate of return, is bigger than 1? Well, that would be equivalent to this present value function having a unique positive root. If I graphed it, in a plane that I'll label the horizontal axis with V, this is a function of V, and the vertical axis with PV for present value, if I graph this function and it had one unique spot where it crossed the positive V axis, that is going to correspond to there being one unique value of I bigger than negative 1. Why? Well, it's because of the general equation relating V and I. Remember I said that if I is your interest rate like 0.1, 1 over 1 plus 0.1, 1 over 1.1 would be what V is. That's the 0.90 repeating. When I is, again, 0.1, 1 plus I is 1.1. Take its reciprocal, you get 0.90 repeating. If I were 0.2, 1.2 is 1 plus I. Its reciprocal is 0.83 repeating, with the 3 repeating. About 83% would be the value of V there. That's an equation relating V and I, no matter what, as long as I is not -1. You don't want to divide by 0. And I being bigger than -1 in this equation is equivalent to V being positive. Think about it. Certainly if I itself is positive, 1 over a positive number is positive, but even if I were negative, say -0.5 or -0.9 or -0.99, this would still be a positive quantity here for V. So showing there's a unique value of I, effectively making this present value 0, is equivalent to showing there's a unique positive value of V that makes it 0. A unique value of I bigger than -1 is equivalent to a unique value of V positive. But what does the graph of this function look like? Well, one thing you could certainly say is it's got a negative intercept here. If you plug in V equals 0, all these terms that involve a V go away. They all become 0. And you're left with just -150. So the graph certainly goes through this point here where the present value is -150, which doesn't sound good. You wouldn't want a present value that's negative, would you? Well, don't worry about that. We're just, again, thinking of this as a function of V. Now, you could plug in something specific for Y. You could try to plug this into your calculator, but that would be a big pain. But you don't need to. Now, this graph very, very well may go down for a while, but I claim it's got to come back up. It's got to come back up and cross this V-axis. Why? How do I know that? This quantity here is positive, and this is where my assumption that it's strictly bigger than 741.2000 is handy. This coefficient of V to the 24th, the highest power of V, is positive. All the coefficients of the other things are negative. Doesn't matter. Because that's the highest power of V, this is eventually going to win out over all the other things, over all these negative quantities. This positive quantity is going to be much bigger than all of them put together. And that's going to mean the function value is eventually going to be positive. This graph has to come back up. And it's got to cross the horizontal V-axis where V is positive somewhere. That's the key point right there. Is it unique? Is there only one such a point? Yes, there is. And you could use an argument based on the fact that this quantity is going to be monotonically increasing in V, meaning always going up as V increases. Monotonically, kind of a big word there, monotonically increasing in V. So there's no way, what I'm saying, there's no way once it crosses once that it could come back down again before it crossed again. Okay? That's one argument you could give. You could also give an argument based on something called Descartes' rule of signs. You could look this up. Descartes' rule of signs that says as you look at this polynomial, which is written from lowest degree to highest degree or from highest degree to lowest degree, there's only one change in sign of the coefficients, from negative to positive in this case, from here to here. And in that case, Descartes' rule of signs actually says there will be a unique positive real root. So that's also something you can invoke if you want. Okay? All right, that's part A. What about part B? Find the minimum value of Y that guarantees a unique positive monthly yield rate. Positive, not just bigger than -1, but positive. And then, then solve for that value of Y. We actually have to solve for it. We can, once again, think about this equation here. So this was part A here. Part B, we once again think about this equation. V equals 1 over 1 plus I. Before we thought about I being bigger than -1. I being bigger than -1 was equivalent to V being positive. Now we think about I being strictly positive. I being positive here is equivalent, if you think about it based on this equation, to V being between 0 and 1. We already knew it was positive. Really the key thing here is that it's less than 1. Why? Well, plug in a positive number. Certainly if you plug in I equals 5, for example, you get 1/6 here, which is positive and less than 1. Even if you plug in a small value of I that's still positive, like 0.1. I is 0.1, we saw that 1 over 1 plus I is 0.90 repeating. It's still less than 1. Any positive value in I here will correspond to a value of V that is not only positive, but is also less than 1. We're after a unique positive monthly yield rate. Effectively, we're after a unique value of V that's less than 1. What value of Y, what minimum value of Y will guarantee that, at least if Y is bigger than that minimum value? Okay, think about this here. I like V to be a unique negative number, or unique number less than 1 here. What I'm going to do to figure out the corresponding value of Y that makes it happen, though, the minimum value of Y, is I'm going to think about the extreme case. What if V equals 1? Go back up to this present value discount factor function and plug in V equals 1. What do you get when you do so? You get negative 150, minus 1.2, minus 1.2, minus 1.2, etc., minus an 11.2, minus 1.2, etc., minus 11.2. 1 to any power is 1. I'm using that fact here, etc. At the end, I get a Y minus 741.2. I could write all those things out, but I could also figure out what they are. How many negative 1.2s are there? Well, there are 6 of them here. Well, actually, if we sort of, okay, let's think of it this way. If we think of all the negative 1.2s as being in all these months put together here, the negative 1.2 for the last month is already taken care of. There's 23 of those, including the months where we have to pay taxes. So I'm going to subtract 23 times 1.2. There were 2 months where I had to pay taxes of 10,000. So I'm going to subtract 2 times 10 as well. And then when I plug in V equals 1 here, I get plus Y minus 741.2. This, in general, is what f of 1 is. Let's simplify it. This simplifies to, let me just go ahead and add these numbers, and I'll put a negative sign in there after adding them. 23 times 1.2 is 27.6, plus 150, plus 20, plus 741.2 is 938.8. Now think about this here. If Y is 938.8 thousand, that's going to make f of 1 0. That's going to mean when V is 1, that's when the present value is 0. So if Y is anything bigger than that, Y is bigger than 938.8, like 940 or 950 or 960 or 970, then f of 1 is positive. In this graph, 1 would be like right there, and we'd have a unique value of V less than 1. So setting this equal to 0 and solving for Y to get 938.8 thousand dollars or euros or whatever is the answer to question B. That is the minimum value of Y that's going to guarantee a unique positive monthly yield rate as long as Y is actually bigger than that minimum value. If Y is anything bigger than this, then this is going to be positive, which means the graph is going to look like this, which means there's going to be a unique value of V less than 1, where this has a root, which means there's going to be a unique value of I bigger than 0, where it has a root. Okay, that's a lot to take in. That's the mathematical part of this. You may want to rewatch it if it interested you enough to want to watch it again. We're going to now move on to doing the spreadsheet and actually calculating the yield, the internal rate of return for various values of Y, and also convert those to what are called nominal annual rates. All right, now we're on to the spreadsheet portion of this video. I'm using Excel. You can use other spreadsheets like Google Sheets, and it's pretty much the same. We're going to compute the IRR as an effective monthly rate. Also, this is the same as the yield rate. We'll also convert that to a nominal annual rate just by multiplying by 12. We will calculate the present value monthly discount factor to illustrate the idea of that function from the first part of the video. Here you can see I've got the given information. I've got the down payment of $150,000. I've got the outlay per month of $1,200. Got the annual taxes of $10,000. I've got the loan balance at the end of 2 years of $741,200. So I want to calculate the IRR here and show you how to do that, but I also want to illustrate capabilities of spreadsheets in doing so if you've never used a spreadsheet before. I picked a sales price of $1 million here, but I'm going to change that. And in fact, that's one thing I want to illustrate with the spreadsheet is what happens if you change these amounts. Can you make everything else over here and over here get updated correctly? I want to show in this column here, I want to show the net inflows. And ultimately the discounted net inflows where I multiply by powers of v as well, effectively illustrating the coefficients of the polynomial function that we talked about. All right, so how do I get these net inflows to Smith here into the spreadsheet? Now, at time 0, it's the down payment, negative $150,000, which of course I could just type in negative $150,000. However, I want to illustrate capabilities of spreadsheets, including the capability to make changes in one spot and again have them affect everything else correctly. To do so, I need to make use of spreadsheet formulas, which always start with an equal sign. Put an equal sign. That's telling the spreadsheet you want to use a formula. If I want to pull down the amount from cell B3 that's in column B in row 3, this 150,000 with a negative sign, I can type equals negative B3 here. So that's referring to the number that's in cell B3, and if I enter this, I will see a negative 150,000. So that's good. That's the down payment that Smith made for buying the property. What about time 1? I want to pull down the net outlay, that 1,200 there with a negative sign. I can type equals negative B4. However, in doing so, it's not going to be most ideal. Let me show you what I mean. I will get a negative 1,200 there, but what I'd like to do now is I'd like to save time. I'd like to copy and paste this downward. However, the spreadsheet is set up in such a way that if I do so by clicking and dragging here like this, I don't get the right numbers here. Why not? Why not am I not getting what's in cell B4 with a negative sign like I typed here? Because the spreadsheet is programmed so that if you copy and paste a formula downward, the number after the B gets updated to first a 5, then a 6, then a 7, then an 8. If I go to these other spots, these other cells, and highlight the formula, you can see it's a negative B5 for that one, and a negative equals negative B6 for that one. I never type those things. The spreadsheet was programmed to update those formulas by updating the numbers as I go downward. That's a good thing in general. However, it's a bad thing here. I don't want that to happen here. So how do you, is there a way to work around it? Yes, there is. And it's to use, excuse me, a dollar sign. The dollar sign doesn't stand for money, it stands for a symbol telling the spreadsheet to fix the cell reference. Now if you put a dollar sign in front of the letter representing the column, that fixes the column. If you put a dollar sign in front of the number, the 4 in this case, that fixes the row. So if I do this dollar sign twice in this way, that will fix that column and that row, cell B4, as I copy and paste downward. Technically speaking, since I'm copying and pasting downward instead of to the right, say, I really only need the second dollar sign in front of the 4 to fix the row, not the column. The column would automatically be fixed. But it's a pretty rare thing where you need to think about that kind of thing, and to play it safe, it usually doesn't hurt to put $2 signs like this to fix both the column and the row. Now as I copy and paste, as I click and drag, this gets copied and pasted correctly to all be negative 1200s, to all pull from the number in B4. Here you can see it's a negative B4 there. Here you can see it's a negative B4 there, etc. Now at time 6, I do not want the negative 1200. Instead, I want 10,000, negative 10,000 minus 1200. I really want negative B4 minus negative, or minus B6 with dollar signs. Oops, B5, excuse me. That'll be negative 11,200. Correct in this row for time 6. Copy and paste it to time 18, which is row 28. And now I got those numbers correct. Copy and paste the negative 1200 formula into the other cells, 7 through 17. I'm just copying and pasting here. And 19 through 23. And finally, in cell B34, which corresponds to time 24 after 2 years, I want to take Y, which again I'm just taking to be a million. I could have picked something else, minus the loan balance. B7 minus B6, and I do not need dollar signs because I'm not going to copy and paste, equals B7 minus B6. I should say here that the answer key to Broverman's book at this point differs from me, and they didn't take into account the extra $1,200 payment. At this point, they put $260,000 here, and it leads to an IRR that is different slightly than the IRR I'm going to get, and is also different from the IRR in the back of the book. However, to be consistent with the earlier parts, I think I should do it this way. I should include that $1,200 as part of this $741,200, just like I did in the first part of the video. All right, we are now ready to compute the IRR as an effective monthly rate, and it's actually pretty easy. Once you've got these net inflows, which combine negative quantities and positive quantities, it's a built-in spreadsheet function. You just type equals IRR, and the syntax here, it's kind of small. If you can see that says values. I need to highlight the values, which are in cells B10 through B34. Notice it typed for me B10 colon B34. I could have typed that by hand. Those are the values. I also need a guess, put a comma, guess for this effective monthly rate. Oh, like how about 2% or something like that. So this is the syntax for computing this IRR, this yield, as an effective monthly rate in the situation. Highlight your inflows. That's the combination of negatives and positives, and use this IRR function like this. It's giving it back to me to the nearest whole percentage, but I can increase the number of decimal places by pressing this button. And again, this is slightly different than the answer in the back of the book for Broverman's book for the 7th edition. Okay. Now again, the benefit of this doing the formulas is I can make changes. What if the sale price goes down to $950,000 instead of $1 million? This IRR should be smaller, and it is 0.26%. What if it's, what about the answer from part B, 938,800? What would you predict for the IRR? 0. I hope you predicted that it would be 0. Yes, that's the minimum value of Y that gave you a positive yield, meaning if Y was bigger than that, we got a definite positive yield. If I make this a 900, for example, here at the end, we get a slightly positive effective monthly yield. Maybe even an 801 for fun here. Yes, a slightly positive effective monthly yield, IRR. Let's go back to $1 million now. Go back to the answer there. Yeah, the book does assume Y is $1 million in the second problem here, 5.1.8. To convert this to a nominal annual rate, all you do is multiply it by 12. So I can type that. Nominal means in name only. It's not really the true yield. It's an approximate annual yield, you might say. The more important yield is the effective monthly yield. But anyway, there it is as a nominal annual yield. As a decimal, you can click the percent button to change it to a percent and increase the decimal places like that. Let's also compute the present value monthly discount factor, V. The formula is 1 over 1 plus I, like I showed you. I is the yield, the IRR, in cell D4. I can just click on that, use parentheses. I'll get V. This is going to be less than 1, a little bit less than 1, 0.9874. I can convert that to a percent if I like. I can increase the decimal places if I like that. Let's now compute the discounted net inflow numbers. What these really are is these coefficients of the polynomial times the corresponding powers of V. I'm going to do it with a formula. It's going to be a little tricky. I need to take the coefficient itself, in cell B10 in this case, this is the constant term actually, times V, which is in cell D6, to the power that's in cell A10, which is going to be the 0 power at time 0, which is, when you raise a number to the 0 power, you get 1. But let's go ahead and type it in as a formula anyway. I want to keep the B10 without dollar signs because I want to copy and paste that down to become a B11, B12, B13, etc. But the V in cell D6, I want to stay fixed from cell D6. So there I use dollar signs. raise it to the A10 power. Do not fix that one. I want that to get updated to a first, second, third, fourth power, etc. So I got the coefficients of the polynomial function from earlier in the video to the various powers of v here. When I raise v to the 0 power, I get 1, so this is negative 150,000, but as I raise v to higher powers, I get smaller numbers. These numbers get closer to 0. And I can discount all these things here, including the positive quantity at the end. Ignore that. And so those are all the discounted numbers. And the interesting thing here is if I add up all these discounted numbers based on the corresponding to the IRR, I should get 0. So let's see if I do that. I'll just do that here. Equals sum, S-U-M, add up all the numbers, cell C10 through C34. This should give me 0. Okay? That's because that's the definition of the IRR, the yield rate. It was where we got a positive root for that present value function. Well, we want the present value to be 0. We were setting that equal to 0. It works no matter what, as long as you calculate v correctly here, no matter what these things are. Let me make one more change. What if you sold it for $2 million? Wow, amazing appreciation. You should expect a huge IRR, relatively speaking. As a monthly rate, that's a really big number. As a nominal annual rate, it's a really big number. The V is smaller. These discounted cash flows get closer to 0. This is still effectively 0. That E negative 10 means that's scientific notation for 10 to the negative 10 power. This is still effectively 0 for the sum of these numbers. Okay, so that's a pretty cool application and introduction to a spreadsheet if you've never seen it before. Thanks for watching.